The purpose of this lesson is to determine a method that we can use to determine the side lengths of any two sides of a triangle when only one side is given. Now, the triangle has to be one of two types of special right triangles. One type of special right triangle is the 30 degree, 60 degree, 90 degree triangle. And the second type of special right triangle is a 45 degree, 45, and 90 degree right triangle. Now these are special because the angle measures, no matter how large the triangle is, the angle measures are always the same. There's always a 30 degree, always a 60 degree, and one right angle within that triangle. So, for example, to prove our method, for our 30, 60, 90 degree right triangle, we prove this method by taking an equilateral triangle that has three equal sides, and we cut it in half. So we're actually going to just cut it right in half. So we're actually going to cut this triangle right down the center, but my pen doesn't want to work. So I'm taking this equilateral triangle and I'm cutting it right down the middle. And my drawing looks a little suspicious, but you gotta work with me here. Okay, so when I cut this equilateral triangle right in the middle, I create a right angle. And if you recall, since it's an equilateral triangle, each of these angle measures here must be 60 degrees originally. And so if I cut this one in half, I have made it a 30 degree angle. And therefore there is our 30 degree, 60 degree, 90 degree angle. Now, for our other special right triangle, it's a 45, 45, 90 degree special right triangle, and that comes from taking a square. Notice I have my side lengths of my square marked with the length of S. Okay, so we're just going to say it's a square of side length S. And I'm going to take that square and I'm going to cut it diagonally right through the middle. So I'm bisecting that square. And so now this is my 45 degree angle. Likewise, this is 45 degrees. And then I have my 90 degree angle in my corner. So on the next pages, I'm going to look at each special right triangle separately. So here we have our equilateral triangle. Notice we have our three equal angles and three congruent sides, all marked with the length of S, and I have cut it right down the center. And so that leaves me with this little triangle over here, and here's my side S from the equilateral triangle, side S, and since I've cut it right in half, this has to be 1/2 of S. Now, since it's a right triangle, we can use the Pythagorean theorem, but I don't know about you, I would much rather not deal with this fraction right here. So what I'm going to do, so that we don't have to deal with the fraction, is I'm going to multiply everything by 2, so to speak. And so that's going to let me draw this 30, 60, 90 right triangle, and I'm just going to call that S. And since this is S, this must be 2S. I guess I should use my cursive S's so it doesn't look like 5. But the question is, what is this length here for this third side? So as always, we know we can use the Pythagorean theorem, and I'm just, for simplicity's sake, going to call that B. So recall the Pythagorean theorem, that we can say a squared plus b squared equals c squared, and in this case we have, we have s squared, that's this side, plus b squared equals 2s quantity squared. That's our c. There's our c. A squared plus b squared equals c squared. So s squared plus b squared, nothing we can do there. But 2s quantity squared, we can make it become 4s squared. And then we're going to combine the s's together, the s squared terms. So I want to solve this for b squared. And then I'm going to take the square root of b squared. So I'm subtracting 2s squared from both sides. You'll have to forgive me, I'm getting used to this program. So when I subtract s squared from 4s squared, I get 3s squared. And now I'm going to square root both sides to solve for b. And I end up with b equals s times the square root of 3. Because remember, I can take this s squared out from underneath my square root sign. And the square root of s squared is s. So that allows me then to come back up here, and I can say that b is equal to s square root of 3. And so therefore, I can redraw my triangle here. Hope you don't get seasick watching what I'm doing here. So this is our 60 degree. One of these two angles has to be given. And I'm going to say that everything sort of depends on this short side of this right triangle. We'll call that S. We know the hypotenuse is twice the length of the short side, and the longest leg is S times the square root of 3. Okay, so now we're going to go through 3 examples of solving a 30, 60, 90 degree right triangle for the remaining side lengths. Now remember our model. We had, okay, not a good triangle, but if I label this 60 degrees here, we're good to go. Okay, remember, this short side is S. This is 2s, the hypotenuse is 2s, and the long leg is s times the square root of 3. So when I give you an example, and I only label the short leg here, I can automatically, I notice that we have a 30 degree angle there, which means that this angle here is 60 degrees. And so then I can say, well, the hypotenuse is twice the short leg, it's 10, and the long leg is 5 square root of 3, and we are done. Super simple. Okay, now, so what if I give you the length of the hypotenuse? Well, the length of the hypotenuse, I know, is twice the length of the short side. So if 16 equals 2s, then s must equal 8. And everything depends on the length of the short side, so I know my long leg is 8 times the square root of 3. Is it really that simple? Well, let's check it. Let's do a check. And we know that a squared, in this case, is 8 squared, plus b squared, so 8 square root of 3 quantity squared, should equal 16 squared. Okay, 8 squared is 64, plus 64 times 3 equals 256, is 16 squared. So if we do the math, you'll find out that 64 times 3 plus 64 is 256, and that does equal 256, obviously. Okay, so it does work, and it really is that simple. Okay, hardest thing. What if I give you the length of the longest leg? Well, again, we know that the ratio of our sides of any 30, 60, 90 right triangle is s root 3, and 2s. So if I say, I can set this equal to our s root 3. So let's do that. 7 equals s root 3, and so to solve for s, we're going to divide both sides by the square root of 3, and we will get 7 square root of 3, which for good mathematics, let's rationalize that denominator by multiplying top and bottom by the square root of 3 over the square root of 3. Remember rationalizing your denominator. The square root of 3 times the square root of 3 equals 3, and this becomes 7 root 3. And so that tells us that if this side of this triangle, 30, 60, 90 right triangle, is 7, then the short side is 7 root 3 over 3, and then we want to multiply to get 2s. 2s is equal to twice 7 root 3 over 3, which will give us 2 times 7 is 14 root 3 over 3. And it looks awkward, but if you put it into your calculator and get a nice decimal, it'll make some more sense than this exact answer that we have. But nevertheless, that was some pretty basic arithmetic that we did to get the lengths of all of our sides. Okay, moving on to our 45 degree, 90 degree right triangle. Remember where that came from. That was cutting diagonally a square. And so here we have our square, and because it's a square, we know that the sides of a square are all equal, so the question only remains, what is the length of our hypotenuse here, which we're going to call C. So again, we're going to use a squared plus b squared equals c squared. 2s squared equals c squared. Square root both sides, and we end up with, we can take this one out, s times the square root of 2 equals 3. And we don't have to worry about the plus or minus in this case because it doesn't make sense for a length of a triangle to be negative. So our model for our 45 degree right triangle, special right triangle, is going to look like this. Whoops, that looks like a 30, 60, 90, so I'm going to mark it 45, and so because I said it is a 45 degree angle, and so this would be, our model will be s, and s times the square root of 2. And so let's go to some examples of our 45, 90 degree right triangle. Okay, I forgot to put my side lengths here, so let's call it 6. Okay, so if that side's 6, that means that this must be 6, and this is 6 times the square root of 2. It is that simple. Let's prove it. Check. 6 squared plus 6 squared equals 6 square root of 2 quantity squared. Well, 36 plus 36 equals 72. 6 square root of 2 squared, I'm going to square the 6 and get 36, times square root of 2 times the square root of 2 is 2. 72 equals 72, and it does work. Alright, let's do another one. You know I'm going to give you the hard example now. So now I've given you the length of the hypotenuse. And so we have to say that, compare it to our model. Our model says that this side is s times the square root of 2, and this side is s, and this side is s. And so therefore, 6 is equal to s times the square root of 2. So we're just going to divide both sides by the square root of 2. And when we get that, s equals 6 divided by root 2, rationalize root 2 over 2, root 2 over root 2, I should say, and that will give us 6 root 2 over 2, and these cancel and become 3 root 2 equals s. And so this 45, 45, 90 right triangle becomes, make sure I get the right, our hypotenuse was 6, and the length of our sides are 3 root 2 and 3 root 2. And this is our 45-degree angle. Okay, you want to check it? Check. 3 root 2 quantity squared plus 3 root 2 quantity squared equals 6 squared. 3 root 2 quantity squared is 9 times 2 is 18 plus another 18 equals 36, and of course it does. Check. 36 equals 36. Okay, so in summary, every 30 degree, 60 degree, 90 degree right triangle has the ratio of the length of the sides of S. 2S is the hypotenuse, because that would be longer than the long leg, and 2 is greater than the square root of 3. So that's how you can kind of remember. You know your hypotenuse has to be the longest side, and everything is based on that short side. On a 45, 45, 90 degree special right triangle, the legs are equal to each other, and the hypotenuse is S times the square root of 2. And you can always figure that out by using the Pythagorean theorem. Hope that helps.